We're going to spend a good couple of weeks on inverse trigonometric functions, okay? Now, I don't know about you, this might seem unusual to you. It did to me when I first learned this, because you guys have been using inverse trig functions on your calculators. In fact, if you get your calculator out, very, very soon after, you learn what the trig functions are, which is in what? Year 9? Year 9, right? You learn how to use them, and you learn very quickly how to use the inverse trig functions. You press shift and then sign, and what kinds of problems did you have that needed those kinds of functions? Do you remember? You'd have like a triangle, wouldn't you? Something like this. Okay? And we've learned from like year 7 and 8 how to find sides. Things like this, 3, 4, 5, okay? But what trig and the trig functions add on to is now you can work out things about the angles, right? So for instance, if I said, okay, there's theta degrees, let's just rehearse this. How would you work out what theta is? You've got actually a whole variety of ways you could do it. What might be the most direct way, most obvious way? You might say, well, look, I've got all the sides here, don't I? So I can use any of the trig functions that I like. Which is the most basic of all the trig functions, by the way? Really? That's interesting. It's sine. It's sine. Sine from which cosine gets its name, from which tan gets its definition. Anyway, so you'd say sine theta, right? You'd say sine of theta degrees is. And then you learn SOHCAHTOA and you're like, oh, okay, that's that. Now, your next step, most of you would not write the next step, but if we were to write it, what would the next step be? It'd be theta degrees is equal to, and then in comes your inverse trig function. Okay, now most of us do not write that because you simply go to your calculator and you punch it in and you get something like 37 degrees. Okay, to the nearest degree. So we've been using these for a long time. What's the big deal? Why are we going to spend so many lessons on this topic? Okay, let me give you 3 reasons. Okay, is this old stuff? No, it's not. And here are my 3 reasons. Maybe you want to jot them down as well. Here's the first thing. You've learned a lot of new knowledge since year 9, right? A lot of new stuff. And that new stuff has a bearing on how we understand inverse trig, and it's going to shed a lot of light. The most important new thing that you've learned is calculus, right? So differentiation, integration, all that kind of thing wouldn't have made any sense if you introduced that in year 9. But now that we know this, when we come to inverse trig, it opens up lots of new avenues to investigate, okay? Secondly, you're going to get a whole variety of new problems. Back in year 9, this was basically all you could do with the inverse trig functions. You could find sides, right? And admittedly, that's useful. But we're going to look, particularly because we know calculus, we're going to look at all kinds of things that relate to change, right? You've got some angle that's changing or something like that. Simple harmonic. Anywhere where trig appears, inverse trig will appear, right? So all these new kinds of problems which we want to look at will require spending more time on this because you use them in a very different way than just simply draw a triangle, okay? Now, one last reason, and it's sort of going to be our launchpad into why today's lesson, even though it's starting this topic, we're not really going to look at trig all that much, is because in the years that you've been using inverse trig functions, you've ignored a lot of the nuances that make inverse trig work. Lots of little details which we've just sort of skirted over and said, don't worry about these, okay? We'll look at them later. Little intricacies about the inverse trig functions which we've more or less ignored, partly because you haven't known a lot of this stuff, okay? So these are my 3 reasons for why we're actually going to spend a fair chunk of time on this, okay? So make yourself a little subheading, which is functions. In order to sort of blow away a lot of all this and put this all together, here's my picture, okay? We've got new knowledge and new problems that we want to approach, okay? So we're going to try and sort of build your understanding of inverse trig and make it sort of bigger and higher, okay? But in order to do that, we have to take your foundations, which you have from year 9, and sort of get rid of them. They're very shallow, okay? If you want to build something very tall, your foundations need to be very deep, okay? I went to University of Sydney when they were building when I was in 3rd and 4th year, they were building a new law building, law faculty building, and it was it's all fancy now. But when I saw it, they were just digging. Like we would joke, every day we would come in and we'd walk along the avenue where all the lecture theatres are, and the hole would just get deeper and deeper, and we're like, where's the building, right? Now the reason is because they wanted it to be quite tall, and so if you want to approach these kinds of new things, you have to take your previous understanding of things, which is just like, don't worry about it. This is just a basic way. You can just use it in a very simple way. If you want to use it in a more complicated way, we have to build deeper foundations, if that makes sense, which is why we're going back to something that's quite basic. You think you know these, we're going to look into a little more depth, okay? Now, what's a function? I'm going to do something with you that I usually do with my year 7s. Let's see how well you fare. That's a great way to introduce something. You're like, great, if I screw this up now, even people 5 years younger than me can't do it. What is a function? Can you define a function? Could you write a sentence for me which starts off, functions are, or a function is? Could you give me a definition? Could you give yourself a definition that you think would be satisfactory? I'll give you about a minute. It doesn't matter if we come up with a whole bunch of different ones. There's lots of different ways to define this that are all valid. Can you write for me a sentence that starts off, a function is, and then fill in the blank? I'm into filling in blanks today, can you see? I give you a minute. Okay. Let's see how we went. Now, by the way, the point is, I just want to see what's going on in there. The more widely different your answers are, the better, in fact, because it'll reveal a lot about us and what we understand. So does anyone want to have a go? A function is, how did you complete the sentence? Yeah, Ren.
A function is a relation that has one output value for each input value.
Wow. Okay. So Mr. Textbook back there has got that. All right. We'll come back to this definition in a second. Does anyone have something a little more like plain language? Because that's correct, but it's very technical. And we learned a lot about functions before we had any of that terminology. Can someone give me what's the simplest definition you can get? Vertical line tester is not a definition. It's a 3-word phrase that is meaningless in this context. Okay? Anyone? Davin, what'd you write down?
A function is something where there's only one x value for every y value.
Okay, alright, hold on. Say that again. So a function is something.
I don't know if something was.
Yeah, okay, alright, we'll get to something in a second. Where
there's only one x value for every y value.
is x values and y values. Okay, so let me just jot this down up here. X values.
No, I'm reading it.
And y values. Okay, we'll come back to that guy. And you said a something. Can anyone give us a better word than a something? Because I think we're on the right track here. But a function is a something that. What could we substitute for that word? Something. Sure, why not?
A function is a relationship between an arbitrary number and another arbitrary.
You guys spend too much time sitting next to each other, clearly. I like the word relationship, though. I think that's a bit of an advance on a something. Though anything's an advance on a something, right? I like to suggest, because this is maths, right? So it is a relationship, but it's a little more concrete than that, right? So I'm going to say a function's a rule, right? A relationship, as a word, has a lot of connotations to it. It's a bit fuzzy. Functions, though, are not fuzzy, right? You'll have, I've heard said 2 arbitrary numbers, an x value and a y value. They might not be x and y though, right? They could be called anything. For instance, they could be called R and A. I'll give an example in a second, okay? This is why we say 2 arbitrary things, I suppose. It's a rule that connects, these 2 things have names, right? We usually call them inputs and outputs. Oops. That is a rule that that connects inputs with outputs. I see 3 pieces here. Okay, and I wonder how you compare to your definition. This is why vertical line test is such an appalling definition. The 3 important bits are, okay, that there is some kind of consistency here. There's a rule. It always does the same thing. It's predictable, right? There is a rule, and then you've got to have these 2 things. They're connected in this way, right? That's what makes it a function. Now, let me draw a diagram for you, okay, to represent this. You've got an input, or inputs rather, right? And you stick them into this box, and the box is the function, okay? The function does stuff to it. That's the rule, right? And it can do a whole variety of things, and then out comes, well, because they come out, that's the outputs, okay? Does that make sense? Now, let's just think of some really quick examples, okay? If you tell me a number, I can tell you what, a square of that number is. Does that make sense? So you give me an input, I give you an output. You can tell me how many chicken burgers you bought in a year, and I can tell you how much you spent on those chicken burgers, right? Because you take your, how many school days are there? I ate 200 chicken burgers this year. So I'll multiply that by, let's actually write that down. Cost equals, whatever, 3.8. 3.8 times chicken burgers. Okay, fine, right? So there you go, there's a function, right? What was the one I said before? I said if you give me a number, right, then I can give you the square, so I don't know, something like that. So maybe that's the number and that's the, yeah, okay. And another example, this is what I was talking about up here. If you give me the radius of a circle, for instance, I can give you its area. What's the function that defines that? That'd be a equals pi r squared. These are all functions, okay? But not all functions are created equal, are they? I picked out these three for a reason. They're not all the same. Have a look at them with me. In what ways are they different? There are some real similarities there, right? Some of you might say, oh, they look identical, right? Apart from what I've named as what the inputs and outputs are, what are the differences? Okay, all right. So you could describe it in terms of what kind of family of functions is in there, right? So this is linear. You can draw it and you get a straight line. These two are not. Okay. But in terms of functions, what would that mean for us? Okay. Well, now here's some important language to get here. Okay. I actually want you to write these three examples down because I'm going to refer to them, give some qualities to them. Okay. This one up here, you called it linear, right? That's true. More generally speaking, it's what we would call a one-to-one function, okay? One-to-one, which is just shorthand for saying one input has one output and only one, right? Only one. Also, one output only has one input, right? If I went the other way, right? If I told you how much I was willing to spend on chicken burgers in a year, you could tell me conclusively how many chicken burgers I could buy, right? And it's not like, oh, there are different solutions to this, right? If I tell you $38, you will tell me 10 burgers and exactly 10 burgers. And it's not like, oh, it might be 9 or it might be 11 or something like that, okay? One input will give you one output, but one output matches up exactly to only one input. Make sense? Okay, now have a look. Have a look at the other two. For instance, have a look at the next one. We can call this one 1, 2, 3.
Pretty clear.
Okay. Now, have a look at 2. Can you see why this is different? This is qualitatively different. It's not one-to-one. Why not? Okay, right. So, start off before. If you give me any number, right? 5, 32, pi, whatever. I will always give you one output. But if I give you an output, you don't know what the input could be because there are options, right? It's not one-to-one. If I gave you 25, I said n was 25, right? Obviously, there's more than one alternative for what x could be, namely plus or minus 5, okay? This is not one-to-one. This is many-to-one. I mean, in this case specifically, it's 2-to-1, but you can think of more kinds of functions where I can give you an output and you're like, well, there might be 2 or 3 or 50 or an infinite number of possible inputs that could give you that output. Okay? Now, I want you to look at this for a second. Don't say anything, just think about it. What's this? What kind of function is it? I've given you 2 kind of categories for what it might be, right? Which is this one? We'll come back to him in a second. Okay. Now, the reason why it's important to distinguish between these kinds of functions is because it affects our understanding of inverse functions. Okay. Okay, so let me wipe this off. What's an inverse function? This is a new little subheading. Yes, don't worry, we're going to come back to it. I'm just deliberately letting it linger. Little subheading for inverse functions. What does invert mean? Invert. Invert?
Inverted.
What does it mean? Like the word, what does it mean?
Inside out.
It generally means you turn something upside down, right? Up, down, down, up. That's when you flip something over. That's inverting. Okay. So an inverse function. An inverse function, it inverts. What are the two things I have here? Inputs and outputs, right? So I'm just gonna turn it upside down. Okay, so what have I got here? I'm going to turn it upside down. I'm going to say outputs. If I stick them into my inverse function, right? Okay, that should give me back the inputs. Okay, so be that there's this inversion, this swapping business, right? How would I take, say, something like this, right? Cost equals 3.8 times chicken burgers. Let's take out the chicken burgers because I can't concentrate and I'm getting hungry. Okay. So if I said here's the function, okay, y equals 3.8x. Okay. There you go. Now it's just a function. What would be the inverse function that corresponds to this? If I were to swap the inputs and the outputs, right? Well, here's the input, right? X, and I'll give you Y. Okay, so I literally just swap them around, right? So if this is the function, then the inverse function, okay, I'll swap them around. I get X equals 3.8Y, okay? But I want it back in terms of Y, right? Because all our functions are in terms of Y. So this is my inverse function, right? Make sense? Okay, now this is fine. This is good. Inverse functions, they take us back where we came from, right? But some kinds of functions, you can't simply do this. It leads us to problems, okay? For example, this one here, right? That's why we said it's many to one. Why is it a problem? Why is being many to one a problem? Let's take this guy over here. What happens when I switch them around? Okay, so again, sorry, I'll put this back in the language that you're used to. Okay, there's a function. So when I switch them around to get the inverse, here's my function, here's my inverse function. Okay, swap them, you get this. Okay, now we said we wanted it in terms of y, didn't we? Right? So if I rearrange this, I have y equals, now what goes on the right hand side? I have to have a plus or minus, don't I? Okay, which accounts for the fact that, you know, there's a many to one thing here. So can you see why this breaks down? This is not a function anymore, okay? It doesn't just take an input and give you an output, right? It takes an input and now I've got two possible outputs, right? So, by the way, give you a bit of language for this. This here is not a function anymore, right? It's actually what we call a relation. This is getting at what Surya chose the right word, actually. Now, these two numbers are still connected, right? There is a relationship between them, but it's not the kind of relationship that a function is. It'll take an input and only give you one output, but this one doesn't do that, does it? Okay, you get an input and you get two outputs at the end. Okay, so this is actually not an inverse function. This is an inverse relation. Okay. Now's the time I'm going to come back to this guy. A equals pi r squared. What kind of function is this? Is it one to one or is it many to one? Let's do this. Let's do it this way. I'm going to count to 3, okay? And then I'm not going to do this hands up, hands down business because that's too easy. You can look across at people and cheat, okay? On the count of 3, I'm going to ask you to say either one to one or many to one. Okay? Don't sit on the fence. Well, there's no fence. It's just one or the other. Okay? You're all busy trying to get some consensus. I better stop you talking. Now, on the count of 3, I want you to tell me which one do you think it is? Is it 1-to-1 or is it many-to-1? Are you ready? Okay? 1, 2, 3. 1-to-1. Success! Yes! Okay. That was almost 50-50. Now that's it. Can you put your hand up if you put 1-to-1? Who said 1-to-1? Yeah, that's about half of you. Okay, hands down. How many of you said many-to-1? Still quite a few, and the rest of you were confused. Okay, fine. You should know when teachers do that to you, it's always a bit of a trick question, okay? Which one is it? Yeah, it's not quite either of them. Now, the question is why. Someone who said it was 1-to-1. Someone who said, no, sorry, I'll start the other way. Someone who said it was many-to-1, why did you say that? Hands up, people who said it was many-to-1, again. No, it wasn't. I have no reason. Okay. All right, regardless, why would anyone? What would be a good, plausible argument for why, because there are plausible arguments, why would you say this is many-to-1? Because there's a square here, and we just said this squared one, right? This one's many-to-1, so logic would say that this is in the same category. All I've done is I've rearranged letters. Okay. A lot of you said 1-to-1. Why? Or what could you argue? Oh, okay. Hold on a second. Radius can't be negative. Why does that change things? Why does that? I mean, it's still a squared thing. Why would that not? Why would that eliminate this problem? What do these look like? What do these look like? If I were to draw my chicken burger graph, okay, 3.8. That's pretty steep, right? So here you go. Now, any way you look at it, right? That's 1-to-1. Okay, I'll draw this guy. It looks like this. Okay. So you can see if I give you an output, I put on the graph, okay, 25. You can see if I go across, there's two values, x values, inputs, that could both give me the 25. That's fine. Okay. Now, what does the graph of this look like? Now, remember, I did tell you, I didn't just give you this equation in thin air, right? I told you what it was. It's the area of a circle, right? Therefore, when you have that information, that tells you this has to look like this, right? There's part of it missing. Why is part missing? Because both area and radius are their measurements, right? So they have to be positive. In other words, you're in the first quadrant, okay? In terms of function language, we would say there's a restriction on this. Okay, depending on the way you say, you could say there's a domain restriction. A domain restriction is about the inputs, right? What's the domain restriction? Yeah, you'd say x must be positive. Aha. Now you see, this is the difference between these two graphs, right? Because there's no restriction here, that's what leads to this problem, right? Oh, I've got many different inputs that could give me the same output. But here, you give me the area, and I will give you the exact radius, and there's not two different types of radius that would give you that area, right? So there's a restriction on this. So what did we say? There's 1-to-1, there's many-to-1. This is not either. It's 1-to-1 with a restriction. Or it's many-to-1 if you forget the fact that it's an area and a radius, and you just say, oh, whatever. Okay. So now let's come back over here. Inverse functions, right? You can get an inverse function out of something if it's 1-to-1, right? If it's many-to-1, you do not get an inverse function, you get an inverse relation, okay? But if you want to take something that's going to give you a relation and you want an inverse function out of it, you stick a restriction on it, okay? And we do this all the time. In fact, we do it with the square root, right? Because, people say, when we want to ask for examples of this, you say, what's the inverse of multiplication? And the inverse of multiplication is division. You say, what's the inverse of addition? And it's subtraction. It inverts inputs and outputs, right? And when you say, what's the inverse of squaring? And everyone says taking the square root, but it's not, is it? Right? It's not exactly. It's only the inverse of part of it when you restrict it. And that's what your calculator does. It doesn't tell you, okay? But that's because the calculator can't give you lots of different possible solutions. So it just takes the positive one. Okay? So therefore, maybe you want to, I'm not sure if you wrote that down. An inverse function inverts inputs and outputs, but you can only do it under these cases, right? You have to make it one-to-one in some way.